Welcome to a lesson with Dr. Powell. Let's take a look at finding the inverse of a matrix using cofactors. First, let's think about how we would use cofactors to find the determinant of the matrix. We select a row or a column, doesn't matter which one, so I've just chosen one, this middle column, and then associated with each entry, we put a sign. How do we determine these signs? Well, we think, how many moves does it take me to get from this position to the top left of the matrix? If it's an odd number, I put a minus sign. If it's an even number, like here to there, that's 2 moves. It's a plus. Here, there's 3 moves. So it's minus. The minus means you're going to change the sign of something, and plus means you're going to keep the sign of something. So what are we going to change the sign of or keep the sign of? What we do is we cross out the column where we are, and then if we're looking at the first entry here, and we want to find the cofactor associated with it, we're going to use this minus, and we're also going to use the determinant of what's left over after I've crossed out the row that it's in and the column that it's in right here, which is this right here. Notice that the 0 is in position C12 of the matrix, where the first index here means the row, and the second one means the column. So the cofactor associated with this position right here, the C12, is minus that determinant. All right, so change the sign of the determinant you see right there, and that's what that cofactor would be. This cofactor is 2. Okay, then how do we find this cofactor? So let's just find the cofactors going down here. So this cofactor here is C22, okay, notated, and it has a plus, and what's kitty corner to it? So we cross that out, and we see these entries, we put them right here. We compute that determinant with that sign, and we get a -2. Okay. All right, then we do the same thing for this position right here by crossing this out and that out, seeing what's left over, it's that, and we're changing the sign because we have a minus there, and we compute that, and we end up getting a -1. So we've actually, by creating this row right here, think of it as a row matrix, a 1 by 3 matrix with the cofactors that correspond to this column, but notice we've written them as a row. This actually is, under the column interpretation of matrix multiplication, is a function or linear transformation from R3. The input is R3, and the output is R, a number. Okay, so, and the output, it will be the determinant of this matrix, assuming that whatever the input is the column right there in the middle, okay? So we've kind of set ourselves up with a function that says, this is what the determinant is going to be. If this is what the input is in this, if the input goes right there in the matrix and these other 2 guys are fixed, okay? Those other 2 guys are fixed. So if we input this guy, we're going to get the determinant. All right, now it's kind of interesting because what if we were to input, like think of multiplying this row matrix right here to the full matrix that we have right here. What would we end up getting? Well, let's think. What we get here is going to be the output when we input this column into this matrix function. So, but when we do that, realize what that means. That means taking the determinant when this guy is right here in the middle. So if we replaced what's in the middle with that guy, so that would look like this: -2, -1, -2, -2, -1, -2, -1, -1, 0. So, and then it's the same thing as taking the determinant of this. Now, guess what the determinant of this is? 2 columns are the same. The determinant will be 0. Various ways of seeing that, but under a volume interpretation, you have two vectors that are the exact same, then one that's not, you're going to be making an area, not a volume. And so that'll be zero volume. Also, if we realize that airdropping or adding one column to another or something like that preserves the determinant, notice that by doing so, you're going to get a column of zeros. And then if you use cofactor expansion right on that column of zeros, you're going to get the a zero for the determinant as well. So it really, so we just get zero. So if we input, so this column right here, inputted would give us a zero. This column is exactly what we saw before, which is the determinant, -4. This one would create a repeat again, right? Because it would be like finding the determinant with this guy put into the middle. So -1, -1, 0, and that's going to be a 0. So notice that this matrix multiplied to this one is that. Now, what if we used a different cofactor expansion along a different column? Let's look at that. Okay, so what if we used cofactor expansion down the first column, but we write it as a row? So notice C11 represents this entry, C21, that's the second row, first entry. So that's that, and that is the cofactor corresponding to that. This is the cofactor corresponding to that. Remember what cofactors are? They're the signed determinants with respect to those positions. So going down the first column, we're going to have a plus, minus, plus for our different signs. So that's what we put right here. And then we find the determinants that are kitty corner for like this one right here. We get by crossing out that. And notice that's what we get. And we do that for this entry and for that entry to give you that, and for this entry to give you that. So you get 2, -1, 1. All right. So that's what's going to be right in here. Now notice that you should get the determinant again by using this cofactor expansion. So if we put this in here and multiply by this matrix, right? Well, the first column, if that's the input, well, that's, remember, we take the dot product of the cofactors from that column with the column itself. So we input this vector into what we've just done with this cofactor expansion, and we should get the determinant. But if we input any others, like this column or that column, we should get zeros out for the same reason that we were getting these zeros right here. It's the same setup. We're just using a different column, same idea. And similarly, if we found the cofactor expansion down this last column right here, like this with the signed determinants, and we matrix multiply this, we should get 0, 0, and then the determinant in the last place. So corresponding to which column we were expanding along. So this one because we're expanding on the first one, that's how we got the cofactors, and then we have zeros elsewhere. Now this is kind of nice because if we're thinking about finding a matrix that that we multiply by that will give us the identity, we're pretty close. Because what if we lined up these rows that we were just looking at and see what we get? This is pretty much the identity. If you were to multiply by -1/4. So in this equation, you can just say -1/4 and -1/4 to both sides. Hey, this would be the identity matrix. Okay, that would be nice. So that's pretty much what we have. So we have -1/4 times this cofactor matrix, which we just determined. So remember what this is: 2, -2, 1 is the first, this guy expanding along the first column. And notice that it's, we're writing as a row, even though these cofactors corresponding this column. These correspond to that column. These correspond to that column, like that. I'm just kind of reviewing where we're getting those from. Okay, so we found the inverse. Formulaically, if you think about finding the cofactors for each position in your matrix, usual notation is like this. The first guy means the first, means the row. So if there's a 1 right here, 1, 1, that means you're in the first row. 2, 2, 2, you're in the second row. 3, 3, 3 means you're in the third row. And then these guys mean the columns, the second entries right there at this particular notation. So this right here, it doesn't look like that. This is actually the transpose of this setup because 1, 2, 3 right there correspond to this 1, 2, 3 right there. Transpose, we switched our rows and columns. So the inverse is simply the transpose of the matrix of cofactors, but then you say 1 over the determinant of the matrix. Because remember, the determinant of the matrix was what we were getting right here in these entries, and that's what we were going to divide by. So 1 over -4 would work. And this is a nice formula for finding the inverse if you want to do it via determinants. It's notice that this formula works well if we can divide by the determinant of A, namely if it's non-zero. If it's non-zero, you can actually always find the inverse right here. If the determinant is 0, we wouldn't be able to find the inverse at all. In fact, working over a nice field, Smith normal form, I mean, we would definitely have a 0 in the diagonal right there. And in the Smith normal form, that means we'd have at least one row of 0, or one column of zeros, meaning non-zero kernel. It's not injective, definitely no inverse. So that's so we have an inverse if the determinant is non-zero. All right, so here's a little example how we can use this setup for finding an inverse fairly quickly for a 2x2, actually. So it's quick because the cofactors corresponding are just numbers. I mean, look at this first position right here. All right, what's the cofactor associated with it? Just -2. So as we're constructing our cofactor matrix, let's just construct it right here. So the cofactor corresponding to 1 is a -2, all right? And the sign associated with this position is just a plus. Okay, let's move down here to this 2. So down in the first column will give us the first row right here of the cofactors of the cofactor transpose matrix. So here we have a -2. We move to here, we just go kitty corner, a 3, but we change its sign, -3. Okay, now we move down this column, all right? So what's kitty corner to this is a 2, but we change its sign because associated with this entry is a minus. So maybe we'll write those out. So plus, minus, plus, minus to help us remember. Let's see, plus, minus. Oh, oops, that's a minus plus. Excuse me, I wrote it wrong. So plus, minus because 1 switch over. Here it's 1 switch over. Here it's 2. Okay, so it's a checkerboard pattern. Plus, minus, minus, plus. Okay, so we determined that, and this entry we determined because we're going down this column right here, and what's kitty corner is the 2, and we change its sign. Okay, now the last position is -2. What's kitty corner to it is a 1, and it's just a plus, so it's just a 1. So that's our transpose of the cofactors, and then we just say -1 over the determinant of the matrix. Determinant of the matrix is simply, let me just erase these signs here so don't have them interfering. Okay. Okay, so we can kind of think about what's going on here. Okay, so the determinant is just -2 minus a 6, so that's where we get 1 over -8. So that's our inverse. Notice that the effect was to simply negate what was off the diagonal. At least for 2x2, this is the effect. I mean, you wouldn't have this effect for 3x3 or 4x4 other sizes, but here the effect was to just negate these off diagonal entries, make them negatives, and then you switch this diagonal right here. Like, see this 1, -2, you just switch them, -2, 1. So this enables us to take inverses of 2x2s extremely quickly. There's not much to do here. We have a nice formulaic way of finding the inverse using this technique. course, it's even simpler for 1 by 1, which is just a single number. The Think about what that is. Essentially, we're just doing this part. We're just saying 1 over it to get to get that inverse, the multiplicative inverse when we're multiplying um, in that particular case. Okay. Well, we'll end here. Um, I guess in the 1 by 1 case, I guess the transpose here of cofactors doesn't really quite work too well, just because we don't really have something that's, if we eliminate the 1, what do we have left to work with? The 1 entry in order to find the cofactor. So really this method starts working truly from a 2 by 2 and up. So 2 by 2 and up, the 1 by 1 case doesn't quite work very well in that case. But just know that the inverse of a number is just its reciprocal, right? Okay, so from 2 by 2 up, we can use this method. Thanks for watching.